In the merge tree family, always happens the same. You define either a partition or a sorting key together with your engine. And whenever you insert data, let's say in this case, we're gonna have these two partitions because we're partitioning by month. We have September and August. ClickHouse is gonna create different parts for each partition, and it's gonna apply the merge logic right when it inserts. If it has to deduplicate, it's gonna deduplicate. If it has to aggregate, it's gonna to aggregate. If it has to sum, it's gonna sum, okay? And then there is a background process. Let me open this again. This is called the merge process. That's gonna take parts, smaller parts from each partition, and it's gonna create bigger parts. And the ones that are already merged are gonna be marked as inactive, okay? So in this case, if we take two small parts, it creates a bigger one, and these other two are marked as inactive. If we take these two bigger parts, they are merged in a bigger one, and they are marked as inactive, the previous one. So parts are immutable, and in the merge process, it applies the merge logic depending on the engine, okay? So for instance, remember if you had, depending on your sorting key, partition key, other settings on the engine, it will deduplicate, aggregate, sum, etc. And this happens continuously. So you have your original data. This is called level 0. Whenever it produces a merge, you have level 1. When there is another merge, it's level 2, etc. Okay, let's see another example. We create this table, partition by month. We're going to insert 3 rows, all in the same partition. And if we look at the system parts, we have one single part for October in level 0. Okay, let's do another insert. What we have now is 2 parts in October, both are active, both in level 0. What if I optimize table hits? This is the same as forcing the merge process. You don't want to do this in production. This is just to show what's happening under the hood. So we are now having just one active part, level 1, and the other two are marked as inactive. Let's try another time. We ingest again. We now have 2 active parts. One is level 0, the other one is level 1. Let's see what happens if I optimize the table. We now have a single active part of level 2. So this is how ClickHouse is doing merges under the hood, so you can have fewer and bigger, smaller parts that are optimized for reads. So this is how the merge tree works. There is partitioning, which defines how data is stored in disk in immutable parts. There's sorting, which specifies how data is sorted inside each part. And then there is the merge process that, depending on the merge tree type, remember replacing, aggregating, summing, creates new immutable parts, usually larger, with the merge logic depending on the engine. These are the 4 concepts you need to take into account when working with merge tree tables in ClickHouse. First, the partition key. This is how data is going to be grouped in disk. You usually choose a time-based partition key or local granularity fields. The goal is having not as much partitions as possible. Then you have the sorting key. This is how data is ordered inside each part. You usually use the columns you're going to use to filter your queries, putting the most selective ones at the beginning. Then you have parts. They are immutable. In disk, each insert can generate multiple parts depending on the partition key. And this is important because it can have a huge performance overhead on ingestion. And then you have merges. This is usually a background process. Do not try to over-optimize. Do not try to run merge yourself. This is something ClickHouse does itself. And it is about taking parts and compact them into bigger parts for more efficient reads. Let me show you an example of a bad partition key. You're going to understand it very quickly. Let's create a hits2 table, and I'm going to partition by date time. The worst you can do. And now let's try to insert in the hits2 table. Let me do this. 10,000 rows, and we're going to have 3 different timestamps. This is good. We take a look at the parts, and we're going to have hits2. We're going to have 3 parts. This is fine. Okay. What happens if we insert in a lot of different parts? So let's try to have 200 different parts. What's going to happen is ClickHouse is going to raise this error, too many parts, because by default, it cannot write on more than 100 different parts, because this is a really bad practice, and it's going to make inserts slower, and it's going to make merge slower. So whenever you have to choose a partition, take into account to take a partition key following some of these rules. The size should be between 300 gigabytes, depending on the engine. For some in replacing, maybe a little bit smaller. Think on how you're going to query your data. So you create a partition key that avoids touching more than few dozens of partitions with your typical select queries. And on insert, a single insert ideally should bring data to one or few partitions. This is how you usually have to buffer data before inserting and have some kind of ingestion proxy that creates proper insertion paths, let's say, okay? And in general, you don't want to have a table with thousands of partitions. You want to have this under control, okay? So for instance, for time series, it's very typical to partition by month or by year. You could also do it by day, depending on your data granularity. And for other types of partitions, you want to have less than 100 partitions, okay? Let's see a quick example on how sorting key and index granularity work. So we create this table, order by user ID and event date with 8,000 rows per granule. And we're going to insert 10 million rows. Now, if we do a count where user ID is this value, we're going to see we are, ClickHouse is reading 32,000 rows, okay? If we take a look at the explain of this query, we're going to see that out of 1,000, more than 1,000 granules, it has skipped all of them except 4, thanks to the sorting key, okay? Because we are ordering this table by user ID, and ClickHouse knows at which position this specific user ID starts in disk, and it can skip a lot of data, okay? What happens if we, instead of filtering by user ID, we filter by event date? Take a look at this. It's processing completely the table, explain indexes 1. The reason about this is event date is in the sorting key, but it's in second position, okay? It's default. Now, what happens if we change the index granularity? Let's create a second table, same sorting key, different granularity. We're going to insert the very same 10 million rows, and now we're going to do the very same query. What's going to happen? It's ClickHouse, it's just reading 4,000 rows, and the reason of this is it's processing the very same 4 granules, but in this case the index granularity is 1000, is gonna read few rows. Okay, very simple rules when selecting the sorting key for your ClickHouse tables. Pick the columns using filtering always. A good rule is putting first the low cardinality columns and then the high cardinality columns. For summing or aggregating merged trees, you have to put all the dimensions in the order by. And for others, replacing, collapsing, anything that has to deduplicate, you just put the primary key inside the order by. Okay, just to understand the storage layout of merged trees, let's go to the disk. So if we go to the ClickHouse folder, inside the data folder, we've been using the default database. So in here we have, for instance, the hits table. Okay, so what we see on each table is we have a folder for each part, and as you can see, the partition is just a logical way to group the data. So we were partitioning by month, so we have one part, a couple of parts for October and another part for November. Okay, and if we go into one of these parts folder, what we have in here is we have all the data in a single binary file. This is because we are using compact parts. You can use wide parts in which every column has a different binary file in disk. Now it's more common to use compact files because they are optimized. The thing is, here applies our data types, our schema compression. So that was why it was important to choose the right data types and so on, because ClickHouse use a binary format. Then we have the primary key, in which ClickHouse stores based on the sorting key of the merge tree. It stores the different values for each granule. We have a separate index for the min max date values, and then we have a marks file which indicates for each position in the primary keys which offset it should read from the binary file with the data. Okay, so this is what ClickHouse stores in disk, and you have one of these set of files for each partition. So this is why it's important to keep under control the number of parts in ClickHouse. This is a table that summarizes what happens when you insert data in ClickHouse. Remember, whenever you insert data, it creates temporary parts on disk. A part is a directory of compressed column files. If you use compact part format, then you have one single file for all the columns on this part. Remember, the merge process combines smaller parts into bigger ones. We have data types and compressions. They are applied per column. Then we have the marks and indexes files. They are the sorting key representation on disk and allow skipping and fast reads. Index is in memory in ClickHouse, so whenever you do a filter, it knows what parts of the data it needs to skip to respond to the index. And finally, there are other operations that happen on insert and on merge. For instance, sorting the data or applying TTLs happens both on insert and on